Okay, we stopped here last time on looking at how 45 versus 54 is not as big a difference as the small blue cylinder that's less than half of the large blue cylinder. And if you look at this one, basically it's still 45 versus 54. The only change is the change in where the x-axis cuts the y-axis. Before it was 40, you can see back here, which is something that Excel does quite routinely, is to truncate your axis for you. And then here it starts at 0. So if you want to de-emphasize the impact of some difference, you can show the whole axis. If you want to emphasize the differences, you can truncate it so that it makes the difference look a lot bigger. So in the study that the book was talking about, one question would be, did exercise cause them to be less tired? Which is kind of counterintuitive. And you would ask, how would you know, at least from this data? And would you have a theory to explain it if it did appear to be so from that data? So data is basically to confirm a theory. So usually experiments start off with literature review, so you have a theory, so you have something to confirm. And since this is one where they took the exercise level that that was pre-existing, whatever people were doing already, it was basically a quasi-experiment, which makes it sometimes a little bit more complicated to assess cause and effect. And different alternatives present themselves, like maybe the people who were less tired were the ones who exercised more, rather than exercise making them less tired. And there could be other things. Since they did self-select, there are other things you're not controlling, like diet. Maybe if they exercise more, they also eat better, they sleep better, they're less overweight, and they get less tired with the same effort because they're stronger. And so all these things are things that vary with the independent variable, and so could be considered confounds, and also a complication in trying to decide cause and effect. And that's why you like to randomize people to groups, is to avoid at least a lot of these confounds. And extraneous variables are just things that are not controlled. If they're just random, if it's like some people are tired, some people are not tired, but they're randomly split into two groups, it's not really a confound. It's not pushing the results in one direction or another. But if they vary with, a group, then they become a confound. And selection is often unavoidable and causes a lot of these problems. Sometimes you can address this with a process called analysis of covariance. And basically, ANOVA is a t-test for more than two groups, but it's a way of determining if two means are different. And then analysis of covariance is taking that procedure and correlating, using correlation to subtract out the effect of something else. So sometimes you might have a pre-test and a post-test. And so one thing that you might want to do is, well, you can analyze the post-test and decide who did better. But you might wonder, well, gee, maybe since my classes weren't randomly assigned to, to where they are, maybe one class was actually just smarter or more prepared or something than the other. And so by taking their pretest and covariating on that, it'll in essence subtract out the difference that was existing there and make your make the results of the part 2, the post test, more accurate. And then replication is the idea that you need to do an experiment more than once to be really confident. Sometimes you can't really control everything, and you can only partially replicate things. So maybe in one case, you do a partial replication and you can eliminate, say, exercise. And on a Navy ship, people are very controlled. So maybe you can eliminate also sleeping the same amount. But maybe the food wasn't as controlled, but in another study, you could do it in a hospital where food is exactly controlled and written down. And so if each time you can do a partial replication and eliminate one or another alternative, then eventually you can kind of weed it down to what you think the real causal connection is. And one of the things about smoking is it's really just not ethical to do a true assign people to smoke or not smoke. But we do see correlations between people that smoke and people that die of certain types of diseases. People that die of these diseases who smoked and they cut their lungs open and they see black stuff in their lungs. We see things like nicotine, which they can put on mice. One of the ways that they've given mice skin cancer is by dripping nicotine on them. And they can use monkeys who are, lungs are going to be a lot like ours, and truly they do assign them to smoke or not smoke in controlled experiments. And with all of these, even though it's a little bit of a jump from animal to human, and all these different ones together, they make us pretty confident. And that's really all that experiments are about, is a confidence level. Even if you do a perfect randomized study, you're still left with a probability statement. P is less than 0.05. We're saying we're pretty confident that this is the cause of the results. And so anyway, you can, by various different methods, arrive at a pretty high level of confidence that something is causing something else without truly doing randomized assignment to groups. But on the other hand, it's generally good to do random assignment to groups if you can do it. And sometimes people misjudge the concept of random. So they think, well, I'll get subjects at random. I'll just go out in the hall and grab people, which really isn't random at all. So you go out in the hall and grab people. If you're out there at 8 a.m., it's a different group of people who are there at 8 a.m. than people that are there at 3 p.m. People that are taking 8 a.m. classes, people that are industrious enough to get up and take 8 a.m. classes, people taking certain classes that are only being held at 8 a.m. So it could be all kinds of reasons why kind of one subgroup or another are going to be in the hall at any particular time of day. And if you were at different buildings, if you were just hanging out in the hall and grabbing people who went by and you were near a nursing class over in the nursing building, or if you were at tech outside engineering classes, you'd have a different set of people, since a lot of nurses are women and a lot of engineers are men. And so to actually be random, one way to do it is to have random number tables. So you take the people as they come in and you randomize them into groups, and you try to pick from as large a selection of the large and representative selection of the population as you can. And there are computer random number generators that use formulas. Sometimes they look at when a number is divided by another number and it runs on a really long time, it eventually becomes kind of random as it gets to be really high number of digits of decimals. There are kind of physical means of being reasonably random, like these lottery machines like we see over on the right. Flipping a coin isn't too bad for just randomizing two groups. And you might have run across things like the I Ching sticks that are in a little kind of a little holder, and you shake them, and you shake them at an angle, and eventually some sticks kind of come out farther than the others. In the data that was reported in the book, there were descriptive statistics, and they were looking at, they divided people up into groups and looking to kind of compare the groups to maybe get a determination on how randomly divided they were. So they cited standard deviation differences, but you can look at those, and if they're not just wildly different, you have to kind of wonder how big a difference is a big difference. And there are sometimes ways to statistically determine that, but generally for this kind of purpose you just kind of inspect them. After a while I get used to what a big difference is. And if you're doing certain types of statistics, sometimes you need to decide to use either like a t-test for assuming equal variances or assuming not equal variances. And so you might be concerned about which one you're using based on how big your standard deviation differences look. Like I mentioned at the beginning of this with sample size, the larger your sample, the more the variations in the sample are smoothed out, the closer the means get to the true normal curve. And even if you start off with a not very normal population, like a skewed population, if you take fairly large samples out of it, you still get a fairly normal distribution in your samples. And then if you have an experiment that not everyone finishes, this is also a concern because they probably aren't going to drop out in a random fashion. If it's a longitudinal study, it's a long time study, men die faster than women. If it's a before and after study and the students have to come back a couple of days later and finish, then the ones that don't come back are probably going to be more lethargic, less enthusiastic, less organized. So the people who come back, the people who don't, aren't exactly randomly distributed. And diffusion of treatment has to do with, we try to not tell people in our experiments, when we just do one subject at a time, we try to not tell them exactly what the study is about, but still they may go back to their classmates and go, I was in this experiment, they had you remember these words, and I still remember blah blah blah, these words. And so it may mean that person gets in your experiment and they've already heard some of those words. So sometimes these things are a problem. And we ask them not to tell people things like that, but you can't always depend on that. So diffusion of treatment is kind of people getting knowledge about your experiment before they get to the experiment. And then within subject designs is, like I've mentioned, of a before and after design. So you would both, before and after, it's the same person taking the test before and after. So you're in both conditions. In our beginning example there, turns out the 5 dead kids were okay, kind of a funny statement, in that they were not really that different. The percentage of dead kids out of the sample was not that different from the percentage of dead kids out of the larger sample of non-ward of the state kids. So it didn't look like a dramatically different or statistically significant difference between the two. And basically, these statistics kind of tell you, when you look at the normal curve, you're cutting off some little percentage. If you have a very extreme score, extremely far from the mean, it cuts off a tiny percentage in the tail. And so 5 dead kids out of the small sample was about the same percentage as the number that they got out of the large sample. So you can compare them on that basis and say the wards of the state were dying off at the same rate as the other kids.